Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xi. In this chapter, chapter 6, we talk about energies and enthalpies. In our previous video, we discussed that the enthalpy change of a reaction is related to many factors, including the coefficients of the reactants and products, and also the status of the reactants and products. Since it's influenced by so many factors, we actually would like to have a standard set of rules so we can make fair comparison between different reactions. And that's what we're going to talk about in this video and with the focus of the heat of formation. So let's first talk about standard states. That's designed because we want to study and compare reactions with under fair rules. So a set of specific conditions called standard states is established. For gas, we talk about that in the ideal gas law chapter. So the standard states for gas is at 1 atm, 0 degrees Celsius, and ideal gas behavior. For solute in a solution, the standard state is 1 molarity concentration, 1 mole per liter as a concentration. For a pure substance, the situation may be a little more complicated. So the standard state is usually the most stable form of a substance that is at 1 atm, and the temperature of interest usually is 25 degrees Celsius room temperature, or 298 Kelvin. Okay, so how do we find the most stable form or elemental substance that is at the standard states? We can refer to handbooks, or we can use our Appendix B, standard thermodynamic values for selected substances. So for each of the substance, we should look for the delta HF that equals to 0. The substance that corresponding to the delta HF equals to 0 is a elemental substance that is at the standard state. For the symbol delta H, superscript degree, subscript F, that degree means this is measured at standard states or standard conditions. Let's take a look at example. Here's a screenshot of Appendix B. Okay, we have 4 different columns. The first one is name of the substance or ion. The second is delta F, delta HF, and then delta GF, delta and S. Okay, so we'll only focus on the second column for now. For aluminum, there are different names of substances. Okay, can be solids, can be aqueous solutions, can be compounds, can be elemental substances. Okay, if we look at the second column, delta HF, only one of them has a value of 0. And that corresponding to the elemental substance that is under standard conditions, standard states. So in this case, aluminum, the most stable form of elemental substance of aluminum is in solid. Okay, in this video, we need to pay close attention to the elemental substances in the standard states. So you need to know what their standard states are for each elemental substance. A few things to keep in mind. The first thing is carbon. When we talk about carbon as elemental substance, the most stable form is graphite, not carbon-60, not diamond. It has to be graphite. Okay, and there are 2 elemental substances have liquid as under the standard states. One is mercury, the other is bromine. A few others of elemental substances are in gas phase under the standard states. All noble gases such as helium, neon, argon, krypton, xenon, and radon. Also, top two elemental substance of the halogen column, that is fluorine and chlorine, plus the 3 common gases, nitrogen, hydrogen, and oxygen. Okay. Besides all of the exceptions I mentioned from graphite, liquid, 2 liquid elemental substances and a few gas elemental substances. All the other elemental substances are in solid under the standard states. Okay, so please remember these rules and determine their states. All right, now we know what the standard states are, and we can talk about the standard enthalpy of reaction, delta H superscript degree subscript Rxn, and the standard enthalpy of formation, delta H superscript degree subscript F. For standard enthalpy of reaction, delta H Rxn, that refers to the enthalpy change of a reaction that is measured at standard states. Okay, any type of reaction, as long as under standard states, is fine. We can use the delta H sub Rxn to refer that. However, for the standard enthalpy of formation, or we can call that standard heat of formation, that refers to the enthalpy change of a reaction that meets the 2 following requirements. Basically, the standard heat of formation have 2 requirements on top of standard enthalpy of reaction. Okay. One of them is the chemical reaction needs to be a formation reaction. A formation reaction refers to that there's only one product that is a compound. The coefficient of the product, the only compound is 1. Okay, and all the reactants should be elements, elemental substances. The second rule is all the reactants for a formation equation are elemental substances that are at the standard states. So then the knowledge of determining the standard states of elemental substances in the previous slides will be useful here. There are 2 things you need to pay attention. One is that the standard heat of formation of an elemental substance at a standard states is always 0, okay? As you can find in the appendix B, it's always 0. And for most compounds, they have a negative standard heat of formation, okay? When we have a negative standard heat of formation means this formation equation is endothermic or exothermic. So when you have a negative delta H, that means, the final minus the initial is negative. The final is smaller than negative. So you need to absorb heat, and that's endothermic reaction. Okay, so just give you a few examples about the standard heat of formation and the standard enthalpy of reaction. So first one, carbon react with gas hydrogen. Carbon as a graphite react with hydrogen gas, 2 hydrogen gas to produce 1 mole of methane that is also in the gas phase. So for this one, it's a formation reaction, and the standard heat of formation is negative 74.9 kilojoules per mole. So you can find the standard heat of formation also in the appendix B for most compounds. When you write the standard formation, please pay attention. Only the elemental substances, only the reactants needs to be at standard condition. For the products, it does not need to be at standard condition. It can be in the gas phase, it can be the less stable form, whatever. It's a product, so you can form anything you want, okay? So if we say multiply the coefficient of this chemical reaction to make it 2 carbon as a graphite react with 4 hydrogen gas to produce 2 methane gas phase. For this reaction, because the coefficient of product is 2, although it meets other requirements that all the reactants are elemental substances and they are under standard conditions, for the second reaction, we cannot call it the standard enthalpy of formation. We have to call it the standard enthalpy of reaction. In this case, you need to multiply the negative 74.9 to make it negative 149.8 kilojoules per mole. So this is actually the stoichiometry calculation we mentioned in previous video. Also, if you see a reaction, titanium 4 chloride as a liquid to react with two water gas molecules to produce titanium oxide as a solid and 4 hydrogen chloride gas. So for this reaction, because the reactants are not elemental substance, for sure we cannot use the standard heat of formation to describe this reaction. If they are all at the measured at standard conditions, we can say the reaction has a standard enthalpy of reaction as negative 25.39 kilojoules per mole. Okay, so let's take a look at a problem. Write a heat of formation reaction. Write a balanced formation equation for each of the following and including the value of the standard heat of formation. A is CHCl3 in liquid phase. B is ammonium chloride in solid phase, and C is lead sulfate in solid phase. Usually, I recommend to have 3 steps to write a heat of formation reaction. So first step is list all the corresponding elemental substance in the standard states as reactants. Status must be included or indicated. So step 2, keep the coefficient of product as 1 and balance the equation. And 3, find the standard heat of formation. In this question, we can use Appendix B for that. So let's walk through all of the 3 questions. For A, CHCl3, it's made of a carbon. So the most stable or the standard phase of carbon is carbon as a graphite, right? And then we have hydrogen as element. So elemental substance of hydrogen is H2 as the gas. For chlorine, the standard states is as an elemental substance is chlorine as a gas. Fluorine, chlorine are in the gas. Okay, so we list all of the reactants and the product. We don't have any other elements in the compound. So we've completed the first step. And second, we need to keep the coefficient of product as 1. So we only have 1 CHCl3 and then balance the equation. So in the product, we only have 1 carbon. The coefficient of graphite should be 1. For hydrogen, we only have 1 hydrogen atom in the compound in the product, but for each of the hydrogen gas, we have 2 hydrogen. So in order to make it balanced, we put half as a coefficient for the hydrogen gas. For chlorine, the same thing. We have 3 chlorine atoms in the compound. So we need to make a coefficient for chlorine as a 3/2. And then we balance the equation, find the standard heat of formation from Appendix B, and list that after the formation equation. So the standard enthalpy of formation for this reaction is negative 83.7 kilojoules per mole. The same thing with B. Okay, so since we have ammonium chloride as a gas, as a solid, we need to first determine the elemental substance of the reactant. For nitrogen, the most stable one is nitrogen gas. For hydrogen is hydrogen gas, chlorine is a chlorine gas. So we can list all the compounds, list all the reactants and the products here. Okay, now we need to balance the equation. Again, the coefficient of the product is 1. So for nitrogen, we only have 1 nitrogen in the product. The coefficient for nitrogen gas, which contains 2 nitrogen atoms, should be half. Then in total, we have 4 hydrogens, make coefficient of hydrogen gas as 2 and chlorine as half. Find the standard enthalpy of formation of the product, the compound in Appendix B, and we can list the standard enthalpy of formation of this reaction is negative 314.4 kilojoules per mole. Okay, so for the last question, lead it's not one of the few elemental substances we talked about, so it should be in the solid phase in the standard condition. Sulfur should also be solid phase, oxygen then in the gas phase. We can list that as lead solid plus sulfur solid plus O2 in gas phase to produce lead sulfate in solid phase. Then balance the equation. Okay, both lead and sulfur should have a coefficient of 1. Then oxygen should have coefficient of 2 to balance the number of oxygen atoms before and after reaction. Okay, then find the standard enthalpy of formation in Appendix B, listed right after this chemical equation as negative 918.39 kilojoules per mole. All right, so this is end of this video, and you need to know how to write the heat of formation after, by now. So I'll see you next time.